Okay, Chapter 8, our continued discussion of Math 429, History of Mathematics and the Mechanical World of Descartes and Newton. We've talked a little bit about the foundational figures and, in particular, René Descartes' contributions through analytic geometry and ramping up to this discovery of calculus that takes place in the middle of the 17th century. We've started looking at some of the early calculus that comes to us through René Descartes' early discussion, or I guess discovery, of methods that led to finding the normal and the tangent to a curve. But let's move on and talk a little bit more about two other foundational figures in early calculus. One of those is Wallis, and Wallis is able to find a method for integration, or what we would think of as integration today. And of course, the picture sure looks a lot like elementary pictures of integration that are found in calculus textbooks. So let's talk a little bit about Wallis's method for finding the area under a parabola. Let's use the parabola y equals x squared, and we'll find the area from 0 to a variable, I guess, width of a. So switching over now to writing utensils here, let's go ahead and talk a little bit about what Barrow's doing, excuse me, what Wallis is doing. So Wallis's proof, or I guess discovery, starts with this. He notes that, this is a very interesting place to start. He notes that 0 squared plus 1 squared all over 1 squared plus 1 squared can be written as 1/2. And turns out 1/2 is the same as a third plus a sixth. Well, what if we bump this up another level? We said 0 squared plus 1 squared plus 2 squared, and I take that last term and make that the denominator. So 2 squared plus 2 squared plus 2 squared. Well, what do we get there? Then it looks like 1 plus 4 on top, there's 5, and then 4 times 3 on top, bottom, that's 5/12. Oh, so that's the same thing as a third plus a 12th. Oh, sorry, I have a little mistake up here. It's a third plus a sixth. So starting to see some sort of perhaps some sort of a pattern here. Let's go ahead and bump it out one more. 0 squared plus 1 squared plus 2 squared plus 3 squared. That all over 2 squared, I guess I would do 3 squared, wouldn't I, if I was to follow the pattern. 3 squared plus 3 squared plus 3 squared plus 3 squared. So on top we end up with, it turns out 7/18 is the fraction in lowest form. That's the same thing as 1/3 plus 1/18. And now it seems like we definitely have some evidence of some sort of a progression. Let's try just one more level. 1 squared plus 2 squared plus 3 squared plus 4 squared. And then on bottom, I guess I would have the 4 squared plus 4 squared plus 4 squared plus 4 squared plus 4 squared. This is the same thing as 3/8 when written in lowest form, which is the same thing as 1/3 plus a 24th. So it certainly seems like what I get is a third always, and then the next piece has, well, you know, it's sort of 6 times, I guess, the bottom term or the last term in the top. And so what Wallis actually says is that he generalizes this. He says, well, 0 squared plus 1 squared plus all the way out to the nth term squared, all over, if I take that nth term and repeat it n times in the bottom. But that's always going to be equal to 1/3 plus 1 over 6 times n, and I think that's definitely what's going on. 24 is 6 times 4, 18 6 times 3, 12 is 2 times 6, 6 is 1 times 6. And he actually gives a name to this, I guess, jump. He calls it the modus inductus. And so we see kind of early induction argument there, although it wouldn't be as formal as we would like to see in modern mathematics. So he actually uses this later in his proof when he's trying to find the area under x squared from 0 to a. So really he doesn't find the area. What he actually finds is he wants to find the ratio of the area under the curve of y equals x squared from x equals 0 to x equals a. He wants to find that ratio to the area of the circumscribing rectangle. So why don't we just call this I guess a big R. We'll give it a big R as a ratio. So that's really what he's going after in his discussion is a ratio of those two things. So I guess pictorially what we're talking about is, you know, if this is the picture we get, here is A. Well, if this is A and we're talking about y equals x squared, so this would be a squared. And so what is he talking about? If this would be region 1 and region 2, then the R that we're talking about is 2 over 1 plus 2. So that's the sort of thing we're looking for in Wallis, and that Wallis is looking for. And this is, of course, before the discovery of calculus. So, and he splits that region 2 into a whole bunch of triangles. So maybe we'll go back really quick and take a look at the picture and make sure we understand what he's doing. So he splits that area up. Excuse me, did I say triangles? I meant rectangles, a whole bunch of little rectangles of width a over n, depending on how many rectangles, of course, you're going to split it up into. So, you know, in this case, 1, 2, 3, 4, 5, 6 of them. So we'd have some distance a divided by 6 would be the width of each rectangle. Of course, their height would be the height dictated by how high the curve is. So let's go ahead and see if we can make a little bit of sense of how that is related to Wallis's, I guess, series of fractions here, fractional expansion. So let's think about how this works. So if we're looking for R, and we're talking about on top a sum of a whole bunch of rectangles areas. So one way we can think of rectangles areas as being the base times the height, right? So the base of each rectangle is a over n, right? And then the height is however far we've traveled from 0 squared, because of course we're talking about under y equals x squared is our function, right? So at first it would be 0 times a over n squared, and then the next one would be a over n times, well, we traveled 1, a over n and squared it, and then in a width of a over n times a height of 2, a over n squared, because that would be the height. We're out to 2 a over n's, and all the way up to some, I guess, last term, which would still have a width a over n, but its height would then be n, a over n squareds, right? So this would just be simply the base times the height of each one of those little rectangles. And then on the bottom, what we would have is the area of the circumscribing rectangle. Now, instead of each one of those, instead of sort of just simply multiplying base times height, we can think of them as being a sum of rectangles of full height in the circumscribing rectangles. So the base is still a over n, but then the height is going to always be, well, height is the last term squared. It's this one actually. It's a squared, right? So the height of that rectangle is a squared. And I guess we can see that right here. So we'd have that for the first little rectangle, this for the second little rectangle. Of course, all of these are going to be the same because these rectangles were all the same height in the picture we saw. Okay, so the last one, a over n times a squared. So where does Wallis go from here? Well, he notices that he can take an a over n out of the top and an a squared out of the bottom. So let's do that. If I take an a over n out of the top, I get a 0 a over n, I should maybe use large brackets, 0a over n squared plus 1a over n squared plus 2a over n squared plus all the way out to n a over n squareds. And I guess on bottom what would we have? We'd end up with, if I factored out an a squared out of each of these, I'd have a over n plus a over n plus a over n plus all the way out to a over n. And so how does that work itself out? If I take a squared and I divide a over n, divide by a squared, well then it's just 1 over, let's see, so what would that be? A over n divided by a squared would be 1 over a n. So these two combine as 1 over a n. Let's think about how that would work. So 1 over a n, when written in the denominator, would just be an a n. So I'll just leave it in the denominator because it's the denominator I want to sort of really work on. So 1 over a n written in the denominator would just be a n. Now then that's a over n plus a over n plus a over n plus all the way out to a over n, and parentheses on top. My two terms have been combined, so I've just got 0a over n squared plus 1a over n squared plus 2a over n squared plus all the way out to na over n squared. Now think about distributing the a over n. If I distributed it across this set, all I would have would be a squareds everywhere. So that's kind of interesting because it's getting closer to this form that Wallace started with. So we end up with 0a over n squared plus 1a over n squared plus 2a over n squared plus all the way out to na over n squared. And then on the bottom, I would just have an a squared plus an a squared plus an a squared plus all the way out to a squared. So that parentheses there. Get rid of it. Okay, getting closer here to his form. What we really need to work on now is what's in the numerator. So I'll go ahead and square out everything in the numerator. I can see that everything in the denominator has an n squared. Okay, and so let's think about what that means. Everything in the denominator has an n squared. I can just take that out, and then everything in the numerator has an a squared, so I can just take that out. So what, I have an a squared over n squared factored out. And what would be left inside would be 0 squared plus 1 squared plus 2 squared plus all the way up to n squared. Okay, so that would be what we have in the numerator there. Let's take a look and see what we have in the denominator. In the denominator, I can see that everything is just an a squared, so I can factor that out. So an a squared would be leave a 1 plus a 1 plus a 1 plus a, well, all the way up to 1. There'd be n of those because there's one that matches with each of those. Well, sorry, n plus 1 of those, right? And we're getting really close. At this point, we can see that an a squared in the numerator and a squared in the denominator cancel, and the n squared in the denominator can be distributed across that sum to achieve something that looks exactly like what we have over there. So let's see, 0 squared plus 1 squared plus 2 squared plus n squared. And on the bottom, I would just have n squared plus n squared plus n squared plus all the way up to n squared. And by our result earlier, you can see that that's the same thing as 1 over 3 plus, let's see, 6 over n, or excuse me, 1 over 6n, right? And then Wallace argues that that as n gets really big here, So if we choose a large number for n, then this term is essentially going to 0. So for large n, we have this thing approximately equal to 1/3. And so what does that mean? It means that in this particular setting, the ratio of the area that's under the curve is 1/3 of the, I guess, the area of the circumscribing rectangle. So this region 2 is 1/3 of I guess, the area in the circumscribing rectangle underneath x squared. So it certainly feels a little bit like calculus. I think it's really interesting that he starts with this result from, I guess you would say, early induction, and then points to it, basically massages the algebra to where he can use it. And indeed, he gets 1/3 here. I guess the check would be, is this really valid? It certainly seems like it's plausible when we look at the area under the curve, that could be 1/3. It kind of seems like perhaps, yes, that 1/3 would be underneath the parabola. But let's go ahead and see what this means. So in today's notation, what is Wallis done? Well, he's literally taking the interval from 0 to a of x squared, and let's say dx, and he's dividing it by, because he wants to find a ratio of this area to the total area, and the total area, of course, has width a, and then its height is going to be a squared, right? So he's calculated this ratio, the interval under x squared from 0 to a, to the area of the circumscribing rectangle. So let's go ahead and see what that is. Well, we know how to integrate, because of course we're modern mathematicians. So x to the third over 3 evaluated from 0 to a, all over a to the third. Well, that's just going to be a to the third over 3, all over a to the third, which is the same thing as a third. And so indeed he has found the correct value, which we can see took a lot more effort and some jumping, especially in the case here where we have this early induction argument, but it's certainly a valid result. So interesting, Wallis actually had something that looks a lot like integration well before its emergence formally in Leibniz and Newton's discovery of calculus. Let's take a quick break and we'll be back and talk a bit about Barrow's method. Okay, let's take a quick look at another method which emerged prior to Newton and Leibniz's discovery of calculus, and that is Barrow's characteristic triangle method for finding the slope of a tangent line. So something in the area of differential calculus as opposed to Wallis's, I guess, integral calculus result. So this is a very interesting story. Barrow was actually a contemporary of Newton. Barrow was the first to hold the Lucasian chair of mathematics at Oxford, and Newton was his successor. It's an interesting fact that actually mathematics emerged as a formal study, and as a result, a chair was established for, I guess, representing mathematics as a field of study at that university with Barrow. So Newton, being sort of the second in line, took up, I guess, the mathematics cause where Barrow, in a sense, left off. And so it seems quite, I guess, a powerful historical anecdote to see that Barrow was very close to the independent discovery of calculus in this particular picture. So I think I'll switch over to talk about what this looks like on, I guess, in a more formal sense, I guess, on a piece of paper. So how does Barrow's characteristic triangle work, and what's the logic behind it? So when we're talking about Barrow's characteristic triangle, what we're really talking about is an approach to find the slope of the tangent at P. The characteristic triangle in question is, I'll draw it in pink here, is this one, PRQ. And Barrow made an argument that related that triangle to this one, PMT. So the argument was just this, that, let's see, as n, I guess the point n here, this one, as n approaches m, then Barrow argued that we have following. He said that triangle PTM, so this one, was approximately, so I'll put a dot above the similarity sign, approximately similar to triangle PQR, so the pink one. And if that's the case, then when things are similar, we have sides in a common ratio. So what we can establish is that TM over MP would have to be equal to, let's see, QR over RP, which is the same thing as E over A. So this ratio E to A would have to be, I guess, in the same ratio as TM is to MP. And that's the basis that Barrow, I guess, makes for his characteristic triangle and the rest of sort of the work that he does here. And he says that, well, if P x comma y, if B is given by a certain point x comma y, and it's pretty easy to see then that Q is going to be, well, if P is x comma y, then Q is back here, E units, and it's down y a units. So Q would be x minus E y minus a, right? A visitor, I'll have to pause for just a second. So if the point P, x comma y, is given the coordinates x comma y, then I think it's clear that Q would be, I guess, a distance back along the x axis E, so x minus E, and the point Q would be, I guess, below P, a distance y minus a, where this is the distance a. So Barrow's method is to take these terms, right? So so substitute in, I guess, substitute two things. What, x is equal to x minus E, and y is equal to y minus a. Substitute those into, I guess not P, but into f function, f of x comma y, and then what are we going to do? Well, the idea is that we want to know the slope of this curve as n gets close to m. So really, the slope as n gets close to m is a over e. So what do? We substitute these into the function, and then number two, what he does is he rejects all terms in which a or e are, how would I say this, are above the first power. So what am I talking about? I'm talking about things like a squared, or if there's an e to the fourth, or if there's an a to the third. Any of those would be considered to be zero, because again, we're making this very, very small, and this very, very small, so squaring or cubing or fourthing those terms would lead to something even smaller. But you do leave all the terms where e or a is 1, and what that resolves to is that you can then solve for the ratio of a over e. And that's really his method. This is Barrow's method. And I know that's all quite opaque at this point because we haven't looked at an example, but let's do that now so that we get a sense of what's going on. So for inspiration, we'll leave this right here, and then we'll work an example right next door so that we have a sense of how Barrow does this. So let's take a look at one that Barrow actually does in his research, and that is, what about x to the third plus y to the third equals r to the third? So this, of course, is some, this is an implicit equation. It's not an explicit function, so it's an implicit function. So what we're going to do is to go ahead and try to solve this for the slope at x comma y. So let's go ahead and see what we have. So the first thing I would do is I would substitute in x minus e for x and cube it, and I would substitute for y minus a and cube it, and we'd let that be just equal to r cubed, some constant. Okay, expanding out using the binomial theorem, we get quite a big expression at this point. Let's go ahead and take it piece by piece. I'll do the x minus e cubic on one line and the y minus a cubic on the next. So we would get x to the third minus 3x squared e plus 3x e squared minus e to the third plus, I'll go on the next line, y to the third minus 3y squared a plus 3ya squared minus a to the third, and that is all equal to r to the third. So I guess writing compactly on one line, well, the first thing we should notice is that, well, no, I'll go ahead and write it compactly first. X to the third minus 3x squared e plus 3x e squared minus e to the third plus y to the third minus 3y squared a plus 3ya squared minus a to the third equals r to the third. So one thing you should notice is that we do have an x to the third and a y to the third and an r to the third on either side of the equal sign, and those from the statement of the problem are equal, so we can literally just cancel those out. And then what does Barrow do? He says, well, we're going to reject all the terms in which a or e are above the first power. So if a or e are above the first power, so I guess that's this. Let's use the yellow for rejecting all terms above the first power. Well, so this one has an e to the first power, so I don't reject it, but there's an e squared I do reject. There's an e to the third I do reject. Here's an a squared I do reject, and here's an a to the third I do reject those. So what do we end up with? We end up with negative 3x squared e minus 3y squared a's, and that's all equal to 0 at this point. So what are we trying to solve for? Remember, in the characteristic triangle, all we're looking for is the ratio of a over e. So if I want an a over e, I guess a couple different ways we can do it, but I guess I will add the 3x squared e across. So we'll end up with negative 3y squared a equals 3x squared e. I'll divide through by the 3y squared negative and divide through by the e on this side, so a over e will equal, let's see, the 3's will cancel, and I'll get negative x squared on top over y squared on bottom. And this, my friends, is supposedly the slope of the tangent line. At that point P. Well, so how can we check to see if Barrow's actually doing something that's legitimate? Well, we would use modern methods. So let's go ahead and check using the modern method here. So what do we've got? We got x to the third plus y to the third equals r to the third. So an implicit function, I'm going to go ahead and take the derivative both sides, or apply the differential operator d by dx to both sides. And when I do that, I get, let's see, 3x squared dx dx plus 3y squared dx dy, and the derivative of r to the third, well, r is simply a constant, so we get a 0 on that side. Well, the dx over dx is just a 1, so we have 3x squared minus 3y squared this should be dy dx. Backwards. So dy dx, and of course dy dx in our modern notation is the slope that we're after. So I'll subtract 3x squared divided by 3y squared and get a result that dy dx is equal to negative x squared over y squared. So for this particular function, we get that implicit differentiation yields the slope, the tangent line as a function of both x and y. Let's go ahead and take a look at what GeoGebra shows us. So I'll go ahead and minimize this and bring up GeoGebra to take a look at just what did we just do on a real function. If it'll fire up for me, I think it's coming. Perhaps. Well, maybe I need to close this one first. Okay, there it is, finally. Oh, now we're going to open all kinds of versions, aren't we? Let's see. I think I should have it in here as Barrow tangents, and this is actually available to you under the resources for the class. So here's the expression that we just derived. I've picked a point on the curve, and this happens to be the curve for x to the third plus y to the third equals 4. And so 4 is actually this number r, so if I change it, it just changes the shape of the curve. When r is 9, we get something like that. So when I pick a point on the curve, I can find what its x and its y coordinates are here, and then calculate this number, which is x to the third over y to the third, and see if that slope is indeed matching the slope that's given by the line that's drawn geometrically as the tangent to the curve. And indeed, you can see that these two numbers agree quite nicely, regardless of where I put the point. We always get the same exact slope of the line as the expression x to the third over y to the third negative yields. So indeed, it does look like Barrow's method works. I'd invite you to really think about, though, the legitimacy of canceling terms that involve an e or an a power greater than 1, and just think about what the implications are there and how that relates to what we do in the limit setting in differential calculus today. So pretty amazing, though. I think that Barrow had a pretty good start on it here with this characteristic triangle. You have a couple of these problems in your homework for this chapter, and look forward to seeing you when we all return to class on Wednesday after break.